Welcome to the course for an introduction for data science methodology. This is the beginning of a story you'll tell others about for years. Your story won't be in the form you experience here, but rather through the stories you'll be sharing with others as you explain how your understanding of a question resulted in an answer that changed how something was done. During this course, you'll gain in-depth insights into data science methodologies. After you complete this course, you'll be able to describe how data scientists apply a structured approach to solve business problems. And you'll be ready to start creating your own data science methodology stories. You'll master the basics of foundational data science methodology through instructional videos that incorporate a real-life case study, readings, interactive hands-on labs, and practice assessments where you can practice your skills, downloadable glossaries for your reference, and graded assessments at the end of each lesson and the end of the course where you can validate your knowledge. Let's take a more detailed view of the course content. In each lesson within each module, you'll explore two foundational data science methodology stages. In Module 1, Lesson 1, you'll explore the stages, business understanding and analytics approach. In Module 1, Lesson 2, you discover data scientists' work during the data requirements and data collection stages. In Module 2, Lesson 1, you'll examine the work that happens during the data understanding and data preparation stages. Next, in Module 2, Lesson 2, you'll study the modeling and evaluation stages. And finally, in Module 3, you'll focus on the deployment and feedback stages. The case study in the course highlights how to apply data science methodology in the following real-world scenario. A healthcare facility has a limited budget to properly address a patient's condition before their initial discharge. The core question is, what is the best way to allocate these funds to maximize their use to provide quality care? As you'll see, if the new data science pilot program is successful, the facility will deliver better patient care by giving physicians new tools to incorporate timely, data-driven information into patient care decisions. When viewing case study information, use the icons displayed at the top right-hand corner of your screen to help you differentiate theory from practice. While participating in the course, if you encounter challenges or have questions, you can find support and answers and connect with other learners in the course's discussion forums. You're ready for this course if you have basic data science knowledge and you know how to use Jupyter Notebooks. And now, welcome to the course. We look forward to you completing this course, earning a valuable certificate, and continuing your path to a data science career. Welcome to Data Science Methodology Overview. After watching this video, you'll be able to describe the term methodology, relate methodology to data science and John Rowland's contributions to data methodology, identify the 10 stages of standard data methodology, and categorize the questions for 10 stages of standard data methodology. Data science is an influential domain that combines statistical analysis, technological expertise, and domain knowledge to extract valuable insights from extensive data sets. However, despite the recent increase in computing power and easier access to data, we often don't understand the questions being asked or know how to apply the data correctly to address the problem at hand. Using a methodology helps resolve those issues. So, what is a methodology? A methodology is a system of methods used in a particular area of study. A methodology is a guideline for the decisions researchers must make during the scientific process. In the context of data science methodology is a structured approach that guides data scientists in solving complex problems and making data-driven decisions. Data science methodology also includes data collection forms, measurement strategies, and comparisons of data analysis methods relative to different research goals and situations. Using a methodology provides the practical guidance needed to conduct scientific research efficiently. There's often a temptation to bypass methodology and jump directly to solutions. However, jumping to solutions hinders our best intentions for solving problems. Next, let's explore methodology as it relates to data science. The data science methodology discussed in this course is a methodology outlined by John Rowland, a seasoned IBM senior data scientist. This course is built on his professional experience and insights into the importance of following a methodology for successful data science outcomes. As a general methodology, data science methodology consists of the following 10 stages: business understanding, analytic approach, data requirements, data collection, data understanding, data preparation, modeling, evaluation, deployment, and feedback. Asking questions is the cornerstone of success in data science. Questions drive every stage of data science methodology. Data science methodology aims to answer the following 10 basic questions, which align with the data methodology questions. These first 2 questions help you define the issue and determine what approach to use. You'll ask, what is the problem that you're trying to solve? And how can you use data to answer the question? You'll use the next 4 questions to help you get organized around the data. You'll ask, what data do you need to answer the question? Where is the data sourced from and how will you receive the data? Does the data you collect represent the problem to be solved? And what additional work is required to manipulate and work with the data? Then you'll use these final 4 questions to validate your approach and final design for ongoing analysis. You'll ask, when you apply data visualizations, do you see answers that address the business problem? Does the data model answer the initial business question, or must you adjust the data? Can you put the model into practice? And can you get constructive feedback from the data and the stakeholder to answer the business question? In this video, you learned that data science methodology guides data scientists in solving complex problems with data. A methodology also includes data collection forms, measurement strategies, and comparisons of data analysis methods relative to different research goals and situations. As a general science methodology, data methodology consists of the following 10 stages: business understanding, analytic approach, data requirements, data collection, data understanding, data preparation, modeling, evaluation, deployment, and feedback. The 10 questions align with defining the business issue, determining an approach, organizing your data, and validating your approach for the final data design.
Welcome to Data Science Methodology 101, From Problem to Approach, Business Understanding. Has this ever happened to you? You've been called into a meeting by your boss who makes you aware of an important task, one with a very tight deadline that absolutely has to be met. You both go back and forth to ensure that all aspects of the tasks have been considered, and the meeting ends with both of you confident that things are on track. Later that afternoon, however, after you've spent some time examining the various issues at play, you realize that you need to ask several additional questions in order to truly accomplish the task. Unfortunately, the boss won't be available again until tomorrow morning. Now, with the tight deadline still ringing in your ears, you start feeling a sense of uneasiness. So, what do? Do you risk moving forward, or do you stop and seek clarification? Data science methodology begins with spending the time to seek clarification to attain what can be referred to as a business understanding. Having this understanding is placed at the beginning of the methodology because getting clarity around the problem to be solved allows you to determine which data will be used to answer the core question. Rollins suggests that having a clearly defined question is vital because it ultimately directs the analytic approach that will be needed to address the question. All too often, much effort is put into answering what people think is the question, and while the methods used to address that question might be sound, they don't help to solve the actual problem. Establishing a clearly defined question starts with understanding the goal of the person who's asking the question. For example, if a business owner asks, "How can we reduce the cost of performing an activity?" we need to understand, is the goal to improve the efficiency of the activity, or is it to increase the business's profitability? Once the goal is clarified, the next piece of the puzzle is to figure out the objectives that are in support of the goal. By breaking down the objectives, structured discussions can take place where priorities can be identified in a way that can lead to organizing and planning on how to tackle the problem. Depending on the problem, different stakeholders will need to be engaged in the discussion to help determine requirements and clarify questions. So now let's look at the case study related to applying business understanding. In the case study, the question being asked is, what is the best way to allocate the limited healthcare budget to maximize its use in providing quality care? This question is one that became a hot topic for an American healthcare insurance provider. As public funding for readmissions was decreasing, this insurance company was at risk of having to make up for the cost difference, which could potentially increase rates for its customers. Knowing that raising insurance rates was not going to be a popular move, the the insurance company sat down with the healthcare authorities in its region and brought in IBM data scientists to see how data science could be applied to the question at hand. Before even starting to collect data, the goals and objectives needed to be defined. After spending time to determine the goals and objectives, the team prioritized patient readmissions as an effective area for review. With the goals and objectives in mind, it was found that approximately 30% of individuals who finish rehab treatment would be readmitted to a rehab center within 1 year, and that 50% would be readmitted within 5 years. After reviewing some records, it was discovered that the patients with congestive heart failure were at the top of the readmission list. It was further determined that a decision tree model could be applied to review the scenario to determine why this was occurring. To gain the business understanding that would guide the analytics team in formulating and performing their first project, the IBM data scientists proposed and delivered an on-site workshop to kick things off. The key business sponsor's involvement throughout the project was critical in that the sponsor set overall direction, remained engaged and provided guidance, and ensured necessary support where needed. Finally, 4 business requirements were identified for whatever model would be built, namely, predicting readmission outcomes for those patients with congestive heart failure, predicting readmission risk, understanding the combination of events that led to the predicted outcome, and applying an easy-to-understand process to new patients regarding their readmission risk. This ends the business understanding section of this course. Thanks for watching. Welcome to Data Science Methodology 101, From Problem to Approach, Analytic Approach. Selecting the right analytic approach depends on the question being asked. The approach involves seeking clarification from the person who is asking the question, so as to be able to pick the most appropriate path or approach. In this video, we'll see how the second stage of the data science methodology is applied. Once the problem to be addressed is defined, the appropriate analytic approach for the problem is selected in the context of the business requirements. This is the second stage of the data science methodology. Once a strong understanding of the question is established, the analytic approach can be selected. This means identifying what type of patterns will be needed to address the question most effectively. If the question is to determine probabilities of an action, then a predictive model might be used. If the question is to show relationships, a descriptive approach may be required. This would be one that would look at clusters of similar activities based on events and preferences. Statistical analysis applies to problems that require counts. For example, if the question requires a yes or no answer, then a classification approach to predicting a response would be suitable. Machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. Machine learning can be used to identify relationships and trends in data that might otherwise not be accessible or identified. In the case where the question is to learn about human behavior, then an appropriate response would be to use clustering association approaches. So now, let's look at the case study related to applying analytic approach. For the case study, a decision tree classification model was used to identify the combination of conditions leading to each patient's outcome. In this approach, examining the variables in each of the nodes along each path to a leaf led to a respective threshold value. This means the decision tree classifier provides both the predicted outcome as well as the likelihood of that outcome based on the proportion of the dominant outcome, yes or no, in each group. From this information, the analyst can obtain the readmission risk, or the likelihood of a yes for each patient. If the dominant outcome is yes, then the risk is simply the proportion of yes patients in the leaf. If it is no, then the risk is 1 minus the proportion of no patients in the leaf. A decision tree classification model is easy for non-data scientists to understand and apply to score new patients for their risk of readmission. Clinicians can readily see what conditions are causing a patient to be scored as high risk, and multiple models can be built and applied at various points during hospital stay. This gives a moving picture of the patient's risk and how it's evolving with the various treatments being applied. For these reasons, the decision tree classification approach was chosen for building the congestive heart failure readmission model. This ends the Analytic Approach section for this course. Thanks for watching. Welcome to Data Science Methodology 101, From Requirements to Collection, Data Requirements. If your goal is to make a spaghetti dinner, but you don't have the right ingredients to make the dish, then your success will be compromised. Think of this section of the data science methodology as cooking with data. Each step is critical in making the meal. So, if the problem that needs to be resolved is the recipe, so to speak, and data is an ingredient, then the data scientist needs to identify which ingredients are required, how to source or collect them, how to understand or work with them, and how to prepare the data to meet the desired outcome. Building on the understanding of the problem at hand, and then using the analytical approach selected, the data scientist is ready to get started. Now let's look at some examples of the data requirements within the data science methodology. Prior to undertaking data collection and data preparation stages of the methodology, it's vital to define the data requirements for decision tree classification. This includes identifying the necessary data content, formats, and sources for initial data collection. So now, let's look at the case study related to applying data requirements. In the case study, the first task was to define the data requirements for the decision tree classification approach that was selected. This included selecting a suitable patient cohort from the health insurance provider's member base. In order to compile the complete clinical histories, 3 criteria were identified for inclusion in the cohort. First, a patient needed to be admitted as inpatient within the provider service area, so they'd have access to the necessary information. Second, they focused on patients with a primary diagnosis of congestive heart failure during 1 full year. Third, a patient must have had continuous enrollment for at least 6 months prior to the primary admission for congestive heart failure so that complete medical history could be compiled. Congestive heart failure patients who had also been diagnosed as having other significant medical conditions were excluded from the cohort because those conditions would cause higher than average readmission rates and thus could skew the results. Then the content, format, and representations of the data needed for decision tree classification were defined. This modeling technique requires 1 record per patient with columns representing the variables in the model. To model the readmission outcome, there needed to be data covering all aspects of the patient's clinical history. This content would include admissions, primary, secondary, and tertiary diagnoses, procedures, prescriptions, and other services provided either during hospitalization or throughout the patient-doctor visits. Thus, a particular patient could have had thousands of records representing all their related attributes. To get to the 1 record per patient format, the data scientists rolled up the transactional records to the patient level, creating a number of new variables to represent that information. This was a job for the data preparation stage, so thinking ahead and anticipating subsequent stages is important. This ends the data requirements section for this course. Thanks for watching. Welcome to Data Science Methodology 101, From Requirements to Collection, Data Collection. After the initial data collection is performed, an assessment by the data scientist takes place to determine whether or not they have what they need. As is the case when shopping for ingredients to make a meal, some ingredients might be out of season and more difficult to obtain, or cost more than initially thought. In this phase, the data requirements are revised and decisions are made as to whether or not the collection requires more or less data. Once the data ingredients are collected, then in the data collection stage, the data scientists will have a good understanding of what they'll be working with. Techniques such as descriptive statistics and visualization can be applied to the data set to assess the content, quality, and initial insights about the data. Gaps in the data will be identified, and plans to either fill or make substitutions will have to be made. In essence, the ingredients are now sitting on the cutting board. Now let's look at some examples of the data collection stage within the data science methodology. This stage is undertaken as a follow-up to the data requirement stage. So now let's look at the case study related to applying data collection. Collecting data requires that you know the source or know where to find the data elements that are needed. In the context of our case study, these can include demographic, clinical, and coverage information of patients, provider information, claims records, as well as pharmaceutical and other information related to all the diagnoses of the congestive heart failure patients. For this case study, certain drug information was also needed, but that data source was not yet integrated with the rest of the data sources. This leads to an important point. It's all right to defer decisions about unavailable data and attempt to acquire it at a later stage. For example, this can even be done after getting some intermediate results from the predictive modeling. If those results suggest that the drug information might be important in obtaining a good model, then the time to try to get it would be invested. As it turned out, though, they were able to build a reasonably good model without this drug information. DBAs and programmers often work together to extract data from various sources and then merge it. This allows for removing redundant data, making it available for the next stage of the methodology, which is data understanding. At this stage, if necessary, data scientists and analytics team members can discuss various ways to better manage their data, including automating certain processes in the database so that data collection is easier and faster. Thanks for watching. Welcome to Data Science Methodology 101, From Understanding to Preparation, Data Understanding. Data understanding encompasses all activities related to constructing the dataset. Essentially, the data understanding section of the data science methodology answers the question, is the data you collected representative of the problem to be solved? Let's apply the data understanding stage of our methodology to the case study we've been examining. In order to understand the data related to congestive heart failure admissions, descriptive statistics needed to be run against the data columns that would become variables in the model. First, these statistics included Hurst, univariates, and statistics on each variable, such as mean, median, minimum, maximum, and standard deviation. Second, pairwise correlations were used to see how closely certain variables were related, and which ones, if any, were very highly correlated, meaning that they would be essentially redundant, thus making only one relevant for modeling. Third, histograms of the variables were examined to understand their distributions. Histograms are a good way to understand how values, or a variable, are distributed and which sorts of data preparation may be needed to make the variable more useful in a model. For example, for a categorical variable that has too many distinct values to be informative in a model, the histogram would help them decide how to consolidate those values. The univariate statistics and histograms are also used to assess data quality. From the information provided, certain values can be recoded or perhaps even dropped if necessary, such as when a certain variable has missing values. The question then becomes, does missing mean anything? Sometimes a missing value might mean no or zero, or at other times it simply means we don't know. Or if a variable contains invalid or misleading values, such as a numeric variable called age that contains 0 to 100 and also 999, where that 999 actually means missing, but would be treated as a valid value unless we corrected it. Initially, the meaning of congestive heart failure admission was decided on the basis of a primary diagnosis of congestive heart failure. But working through the data understanding stage revealed that the initial definition was not capturing all of the congestive heart failure admissions that were expected based on clinical experience. This meant looping back to the data collection stage and adding secondary and tertiary diagnoses and building a more comprehensive definition of congestive heart failure admission. This is just one example of the interactive processes in the methodology. The more one works with the problem and the data, the more one learns, and therefore the more refinement that could be done within the model, ultimately leading to a better solution to the problem. This ends the data understanding section of this course. Thanks for watching. Welcome to Data Science Methodology 101, From Understanding to Preparation, Data Preparation Concepts. In a sense, data preparation is similar to washing freshly picked vegetables insofar as unwanted elements such as dirt or imperfections are removed. Together with data collection and data understanding, data preparation is the most time-consuming phase of a data science project, typically taking 70% and even up to 90% of the overall project time. Automating some of the data collection and preparation processes in the database can reduce this time to as little as 50%. This time savings translates into increased time for data scientists to focus on creating models. To continue with our cooking metaphor, we know that the process of chopping onions to a finer state will allow for its flavors to spread through a sauce more easily than would be the case if we were to drop a whole onion into the sauce pot. Similarly, transforming data in the data preparation phase is the process of getting the data into a state where it may be easier to work with. Specifically, the data preparation stage of the methodology answers the question, what are the ways in which data is prepared? To work effectively with the data, it must be prepared in a way that addresses missing or invalid values and removes duplicates, toward ensuring that everything is properly formatted. Feature engineering is also part of data preparation. It is the process of using domain knowledge of the data to create features that make the machine learning algorithms work. A feature is a characteristic that might help when solving a problem. Features within the data are important to predictive models and will influence the results you want to achieve. Feature engineering is critical when machine learning tools are being applied to analyze the data. When working with text analysis steps for coding the data are required to be able to manipulate the data. The data scientist needs to know what they're looking for within their data set to address the question. The text analysis is critical to ensure that the proper groupings are set and that the programming is not overlooking what is hidden within. The data preparation phase sets the stage for the next steps in addressing the question. While this phase may take a while to do, if done right, the results will support the project. If this is skipped over, then the outcome will not be up to par and may have you back at the drawing board. It's vital to take your time in this area and use the tools available to automate common steps to accelerate data preparation. Make sure to pay attention to the detail in this area. After all, it takes just one bad ingredient to ruin a fine meal. This ends the data preparation section of this course, in which we reviewed key concepts. Thanks for watching. Welcome to Data Science Methodology 101, From Understanding to Preparation, Data Preparation Case Study. In a sense, data preparation is similar to washing freshly picked vegetables insofar as unwanted elements such as dirt or imperfections are removed. So now let's look at the case study related to applying data preparation concepts. In the case study, an important first step in the data preparation stage was to actually define congestive heart failure. This sounded easy at first, but defining it precisely was not straightforward. First, the set of diagnosis-related group codes needed to be identified, as congestive heart failure implies certain kinds of fluid buildup. We also need to consider that congestive heart failure is only one type of heart failure. Clinical guidance was needed to get the right codes for congestive heart failure. The next step involved defining the readmission criteria for the same condition. The timing of events needed to be evaluated in order to define whether a particular congestive heart failure admission was an initial event, which is called an index admission, or a congestive heart failure-related readmission. Based on clinical expertise, a time period of 30 days was set as the window for readmission relevant for congestive heart failure patients, following the discharge from the initial admission. Next, the records that were in transactional format were aggregated, meaning that the data included multiple records for each patient. Transactional records included professional provider facility claims submitted for physician, laboratory, hospital, and clinical services. Also included were records describing all the diagnoses, procedures, prescriptions, and other information about inpatients and outpatients. A given patient could easily have hundreds or even thousands of these records, depending on their clinical history. Then, all the transactional records were aggregated to the patient level, yielding a single record for each patient as required for the decision tree classification method that would be used for modeling. As part of the aggregation process, many new columns were created representing the information in the transactions. For example, frequency and most recent visits to doctors, clinics and hospitals with diagnoses, procedures, prescriptions, and so forth. Comorbidities with congestive heart failure were also considered, such as diabetes, hypertension, and many other diseases and chronic conditions that could impact the risk of readmission for congestive heart failure. During discussions around data preparation, a literary review on congestive heart failure was also undertaken to see whether any important data elements were overlooked, such as comorbidities that had not yet been accounted for. The literary review involved looping back to the data collection stage to add a few more indicators for conditions and procedures. Aggregating the transactional data at the patient level meant merging it with the other patient data, including their demographic information, such as age, gender, type of insurance, and so forth. The result was the creation of one table containing a single record per patient, with many columns representing the attributes about the patient in his or her clinical history. These columns would be used as variables in the predictive modeling. Here is a list of the variables that were ultimately used in building the model. The dependent variable, or target, was congestive heart failure readmission within 30 days following discharge from a hospitalization for congestive heart failure, with an outcome of either yes or no. The data preparation stage resulted in a cohort of 2,343 patients meeting all of the criteria for the case study. The cohort was then split into training and testing sets for building and validating the model respectively. This ends the data preparation section of this course, in which we apply the key concepts to the case study. Thanks for watching. Welcome to Data Science Methodology 101, From Modeling to Evaluation, Modeling Concepts. Modeling is the stage in the data science methodology where the data scientist has the chance to sample the sauce and determine if it's bang on or in need of more seasoning. This portion of the course is geared towards answering two key questions. First, what is the purpose of data modeling? And second, what are some of the characteristics of this process? Data modeling focuses on developing models that are either descriptive or predictive. An example of a descriptive model might examine things like, if a person did this, then they're likely to prefer that. A predictive model tries to yield yes or no or stop-go type outcomes. These models are based on the analytic approach that was taken, either statistically driven or machine learning driven. The data scientist will use a training set for predictive modeling. A training set is a set of historical data in which the outcomes are already known. The training set acts like a gauge to determine if the model needs to be calibrated. In this stage, the data scientist will play around with different algorithms to ensure that the variables in play are actually required. The success of data compilation, preparation, and modeling depends on the understanding of the problem at hand, and the appropriate analytical approach being taken. The data supports the answering of the question and, like the quality of the ingredients in cooking, sets the stage for the outcome. Constant refinement, adjustments, and tweaking are necessary within each step to ensure the outcome is one that's solid. In John Rollin's descriptive data science methodology, the framework is geared to do three things. First, understand the question at hand. Second, select an analytic approach or method to solve the problem. And third, obtain, understand, prepare, and model the data. The end goal is to move the data scientist to a point where a data model can be built to answer the question. With dinner just about to be served and a hungry guest at the table, the key question is, have I made enough to eat? Well, let's hope so. In this stage of the methodology, model evaluation, deployment, and feedback loops ensure that the answer is near and relevant. This relevance is critical to the data science field overall, as it's a fairly new field of study and we're interested in the possibilities it has to offer. The more people that benefit from the outcomes of this practice, the further the field will develop. This ends the modeling to evaluation section of this course, in which we reviewed the key concepts related to modeling. Thanks for watching. Welcome to Data Science Methodology 101, From Modeling to Evaluation, Modeling Case Study. Modeling is the stage in the data science methodology where the data scientist has the chance to sample the sauce and determine if it's bang on or in need of more seasoning. Now, let's apply the case study to the modeling stage within the data science methodology. Here we'll discuss one of the many aspects of model building, in this case, parameter tuning to improve the model. With a prepared training set, the first decision tree classification model for congestive heart failure readmission can be built. We are looking for patients with high-risk readmission, so the outcome of interest will be congestive heart failure readmission equals yes. In this first model, overall accuracy in classifying the yes and no outcomes was 85%. This sounds good, but it represents only 45% of the yes. The actual readmissions are correctly classified, meaning that the model is not very accurate. The question then becomes, how could the accuracy of the model be improved in predicting the yes outcome? For decision tree classification, the best parameter to adjust is the relative cost of misclassified yes and no outcomes. Think of it like this. When a true non-readmission is misclassified and action is taken to reduce that patient's risk, the cost of that error is the wasted intervention. A statistician calls this a type 1 error or a false positive. But when a true readmission is misclassified and no action is taken to reduce the risk, then the cost of that error is the readmission and all its attendant costs plus the trauma to the patient. This is a type 2 error or a false negative. So we can see that the costs of the two different kinds of misclassification errors can be quite different. For this reason, it's reasonable to adjust the relative weights of misclassifying the yes and no outcomes. The default is 1-to-1, but the decision tree algorithm allows the setting of a higher value for yes. For the second model, the relative cost was set at 9-to-1. This is a very high ratio, but gives more insight to the model's behavior. This time the model correctly classified 97% of the yes, but at the expense of a very low accuracy on the no, with an overall accuracy of only 49%. This was clearly not a good model. The problem with this outcome is a large number of false positives, which would recommend unnecessary and costly intervention for patients who would not have been readmitted anyway. Therefore, the data scientist needs to try again to find a better balance between the yes and no accuracies. For the third model, the relative cost was set at a more reasonable 4-to-1. This time, 68% accuracy was obtained on only yes, called sensitivity by statisticians, and 85% accuracy on the no, called specificity, with an overall accuracy of 81%. This is the best balance that can be obtained with a rather small training set through adjusting the relative cost of misclassified yes and no outcomes parameter. A lot more work goes into the modeling, of course, including iterating back to the data preparation stage to redefine some of the other variables so as to better represent the underlying information and thereby improve the model. This concludes the modeling section of the course, in which we applied the case study to the modeling stage within the data science methodology. Thanks for watching. Welcome to Data Science Methodology 101, from modeling to evaluation. Evaluation. A model evaluation goes hand in hand with model building. As such, the modeling and evaluation stages are done iteratively. Model evaluation is performed during model development and before the model is deployed. Evaluation allows the quality of the model to be assessed, but it's also an opportunity to see if it meets the initial request. Evaluation answers the question, does the model used really answer the initial question, or does it need to be adjusted? Model evaluation can have two main phases. The first is the diagnostic measures phase, which is used to ensure the model is working as intended. If the model is a predictive model, a decision tree can be used to evaluate if the answer the model can output is aligned to the initial design. It can be used to see where there are areas that require adjustments. If the model is a descriptive model, one in which relationships are being assessed, then a testing set with known outcomes can be applied and the model can be refined as needed. The second phase of evaluation that may be used is statistical significance testing. This type of evaluation can be applied to the model to ensure that the data is being properly handled and interpreted within the model. This is designed to avoid unnecessary second-guessing when the answer is revealed. So now let's go back to our case study so that we can apply the evaluation component within the data science methodology. Let's look at one way to find the optimal model through a diagnostic measure based on tuning, one of the parameters in model building. Specifically, we'll see how to tune the relative cost of misclassifying yes and no outcomes. As shown in this table, 4 models were built with 4 different relative misclassification costs. As we see, each value of this model building parameter increases the true positive rate, or sensitivity, of the accuracy in predicting yes, at the expense of lower accuracy in predicting no, that is, an increasing false positive rate. The question then becomes, which model is best based on tuning this parameter? For budgetary reasons, the risk-reducing intervention could not be applied to most or all congestive heart failure patients, many of whom would not have been readmitted anyway. On the other hand, the intervention would not be as effective in improving patient care as it should be, with not enough high-risk congestive heart failure patients targeted. So, how do we determine which model was optimal? As you can see on this slide, the optimal model is the one giving the maximum separation between the blue ROC curve relative to the red baseline. We can see that Model 3, with a relative misclassification cost of 4:1, is the best of the 4 models. And just in case you were wondering, ROC stands for Receiver Operating Characteristic Curve, which was first developed during World War II to detect enemy aircraft on radar. It has since been used in many other fields as well. Today it's commonly used in machine learning and data mining. The ROC curve is a useful diagnostic tool in determining the optimal classification model. This curve quantifies how well a binary classification model performs, declassifying the yes and no outcomes when some discrimination criterion is varied. In this case, the criterion is a relative misclassification cost. By plotting the true positive rate against the false positive rate for different values of the relative misclassification costs, the ROC curve helped in selecting the optimal model. This ends the evaluation section of this course. Thanks for watching. Welcome to Data Science Methodology 101. From deployment to feedback. Deployment. While a data science model will provide an answer, the key to making the answer relevant and useful to address the initial question involves getting the stakeholders familiar with the tool produced. In a business scenario, stakeholders have different specialties that'll help make this happen, such as the solution owner, marketing, application developers, and IT administration. Once the model is evaluated and the data scientist is confident it'll work, it's deployed and put to the ultimate test. Depending on the purpose of the model, it may be rolled out to a limited group of users or in a test environment to build up confidence in applying the outcome for use across the board. So now let's look at the case study related to applying deployment. In preparation for solution deployment, the next step was to assimilate the knowledge for the business group who would be designing and managing the intervention program to reduce readmission risk. In this scenario, the business people translated the model results so that the clinical staff could understand how to identify high-risk patients and design suitable intervention actions. The goal, of course, was to reduce the likelihood that these patients would be readmitted within 30 days after discharge. During the business requirement stage, the intervention program director and her team had wanted an application that would provide automated, near real-time risk assessments of congestive heart failure. It also had to be easy for clinical staff to use, and preferably through browser-based application on a tablet that each staff member could carry around. This patient data was generated throughout the hospital stay. It would be automatically prepared in a format needed by the model, and each patient would be scored near the time of discharge. Clinicians would then have the most up-to-date risk assessment for each patient, helping them to select which patients to target for intervention after discharge. As part of solution deployment, the intervention team would develop and deliver training for the clinical staff. Also, processes for tracking and monitoring patients receiving the intervention would have to be developed in collaboration with IT developers and database administrators so that the results could go through the feedback stage and the model could be refined over time. This map is an example of a solution deployed through a Cognos application. In this case, the case study was hospitalization risk for patients with juvenile diabetes. Like the congestive heart failure use case, this one used decision tree classification to create a risk model that would serve as the foundation for this application. The map gives an overview of hospitalization risk nationwide, with an interactive analysis of predicted risk by a variety of patient conditions and other characteristics. This slide shows an interactive summary report of risk by patient population within a given node of the model so that clinicians could understand the combination of conditions for this subgroup of patients. And this report gives a detailed summary on an individual patient, including that patient's predicted risk and details about the clinical history, giving a concise summary for the doctor. This ends the deployment section of this course. Thanks for watching. Welcome to Data Science Methodology 101, From Deployment to Feedback. Feedback. Once in play, feedback from the users will help to refine the model and assess it for performance and impact. The value of the model will be dependent on successfully incorporating feedback and making adjustments for as long as the solution is required. Throughout the data science methodology, each step sets the stage for the next. Making the methodology cyclical ensures refinement at each stage in the game. The feedback process is rooted in the notion that the more you know, the more that you'll want to know. That's the way John Rollins sees it, and hopefully you do too. Once the model is evaluated and the data scientist is confident it'll work, it's deployed and put to the ultimate test, actual real-time use in the field. So now let's look at our case study again to see how the feedback portion of the methodology is applied. The plan for the feedback stage included these steps. First, the review process would be defined and put into place, with overall responsibility for measuring the results of a flying to risk model of the congestive heart failure risk population. Clinical management executives would have overall responsibility for the review process. Second, congestive heart failure patients receiving intervention would be tracked and their readmission outcomes recorded. Third, the intervention would then be measured to determine how effective it was in reducing readmissions. For ethical reasons, congestive heart failure patients would not be split into controlled and treatment groups. Instead, readmission rates would be compared before and after the implementation of the model to measure its impact. After the deployment and feedback stages, the impact of the intervention program on readmission rates would be reviewed after the first year of its implementation. Then the model would be refined based on all the data compiled after model implementation and the knowledge gained throughout these stages. Other refinements included incorporating information about participation in the intervention program and possibly refining the model to incorporate detailed pharmaceutical data. If you recall, data collection was initially deferred because the pharmaceutical data was not readily available at the time. But after feedback and practical experience with the model, it might be determined that adding that data could be worth the investment of effort and time. We also have to allow for the possibility that other refinements might present themselves during the feedback stage. Also, the intervention actions and processes would be reviewed and very likely refined as well, based on the experience and knowledge gained through initial deployment and feedback. Finally, the refined model and intervention actions would be redeployed with the feedback process continued throughout the life of the intervention program. This is the end of the feedback portion of this course. Thanks for watching.
In this video, we will listen to data professionals talk about the role storytelling plays in the life of a data analyst.
The role of storytelling in a data analyst's life cannot be overstated. It is super critical to get really good at storytelling with data. I think humans naturally understand the world through stories. So if you're trying to convince anyone to do anything with data, the first thing you have to do is tell a clear, concise, compelling story. I also think it can be really useful for the data analyst to develop a story anytime they're working with a data set to help themselves better understand the underlying data set and what it's doing. There's always going to be a balance between telling a clear, coherent, simple story and making sure you're conveying all the complexities that you might find within the data. And I think finding that balance can be really challenging, but is really critical.
The art of storytelling is significant in the life of a data analyst. It doesn't matter how much or what wonderful information you've come up with. If you can't find a way to communicate that to your audience, whether it's the consumer or a director level or executive level person, then it's for naught. You have to find a way to communicate that, and it's usually best to do it in a visual or through telling a story so that they understand how that information can be useful.
I have to say, storytelling is an essential skill set. It's like the last mile in delivery. A lot of people can handle the technical side through a short period of training. However, the ability to extract value from data and to communicate it is in short supply. If you think about the long-term career, I think it's very critical to know how to tell a compelling story with data.
Storytelling is absolutely crucial to data and analytics. This is how you actually convey your message. Everyone can show numbers, but if you don't have a story around it, if you don't have a compelling reason to act, then ultimately what you're presenting isn't going to resonate with your audience. They did a study at Stanford where they had people present their pitches, and in that pitch they had simply KPIs, numbers, statistics, but they also told a story. The audience members were then quizzed after the fact what they remembered from each of those presentations. And it was those stories that stuck with them. Yes, there were still facts and figures contained within the story, but that is the way that you drive it home. Having that emotional connection to the story, to the understanding, to the data is really how you're going to get people to take the action that you want and need them to take.
Welcome to Data Science Methodology 101, Course Summary. We've come to the end of our story, one that we hope you'll share. You've learned how to think like a data scientist, including taking the steps involved in tackling a data science problem and applying them to interesting real-world examples. These steps have included forming a concrete business or research problem, collecting and analyzing data, building a model, and understanding the feedback after model deployment. In this course, you've also learned methodical ways of moving from problem to approach, including the importance of understanding the question, the business goals and objectives, and picking the most effective analytic approach to answer the question and solve the problem. You've also learned methodical ways of working with the data, specifically determining the data requirements, collecting the appropriate data, understanding the data, and then preparing the data for modeling. You've also learned how to model the data by using the appropriate analytical approach based on the data requirements and the problem you're trying to solve. Once the approach was selected, you learned the steps involved in evaluating and deploying the model, getting feedback on it, and using that feedback constructively so as to improve the model. Remember that the stages of this methodology are iterative. This means that the model can always be improved for as long as the solution is needed, regardless of whether the improvements come from constructive feedback or from examining newly available data sources. Using a real case study, you learned how data science methodology can be applied in context towards successfully achieving the goals that were set out in the business requirement stage. You also saw how the methodology contributed additional value to business units by incorporating data science practices into their daily analysis and reporting functions. The success of this new pilot program that was reviewed in the case study was evident by the fact that physicians were able to deliver better patient care by using new tools to incorporate timely, data-driven information into patient care decisions. And finally, you learned, in a nutshell, the true meaning of a methodology, that its purpose is to explain how to look at a problem, work with data in support of solving the problem, and come up with an answer that addresses the root problem. By answering 10 simple questions methodically, we've taught you that a methodology can help you to solve not only your data science problems, but also any other problem. Your success within the data science field depends on your ability to apply the right tools at the right time, in the right order, to address the right problem. And that is the way John Rollins sees it. We hope you've enjoyed taking the Data Science Methodology course and found it to be a valuable experience, one that you'll share with others. And of course, we also hope that you'll review and take other data science courses in the Data Science Fundamentals learning path. Now, if you're ready and up to the challenge, please take the final exam. Thanks for watching.
Welcome to an introduction to CRISP DM. After watching this video, you'll be able to define CRISP DM, list and describe the 6 stages of the CRISP DM model, and explain what happens after the final CRISP DM stage. CRISP DM, which stands for Cross-Industry Standard Process for Data Mining, is an industry-proven way to guide your data mining efforts. CRISP DM is an iterative data mining mode and is a comprehensive methodology for data mining projects which provides a structured approach to guide data-driven decision-making. As a data methodology, a study of the CRISP DM model includes 6 data mining stages, their descriptions, and provides explanations of the relationships between tasks and stages. And as a process model, CRISP DM provides high-level insights into the data mining lifecycle. Like other data mining science methodologies, CRISP DM requires flexibility at each stage and communication with peers, management, and stakeholders to keep the project on track. After any of the following 6 stages, data scientists might need to revisit an earlier stage and make changes. The business understanding stage is the most important because this stage sets and outlines the intentions of the data analysis project. This stage is common to both John Rollins' data science methodology and CRISP DM methodology. This stage requires communication and clarity to overcome stakeholders' differing objectives, biases, and information-related modalities. Without a clear, concise, and complete understanding of the business problem and project goals, the project effort will waste time and resources. Then, CRISP DM combines the stages of data requirements, data collection, and data understanding from John Rollins' methodology outline into a single data understanding stage. During this stage, data scientists decide on data sources and acquire data. Next, during the data preparation stage, data scientists transform the collected data into a usable data subset and determine if they need more data. With data collection complete, data scientists select a data set and address questionable, missing, or ambiguous data values. Data preparation is common to foundational data methodology and CRISP DM. The modeling stage fulfills the purpose of data mining and creates data models that reveal patterns and structures within the data. These patterns and structures provide knowledge and insights that address the stated business problem and goals. Data scientists select models based on subsets of the data and adjust the models as needed. Model selection is an art and science. Both foundational methodology and CRISP-DM focus on creating knowledge information that has meaning and utility. During the evaluation stage, data scientists test the selected model. Data scientists usually prepare a pre-selected test to run the trained model. The test platform sees the data as new, and data scientists then assess the model's effectiveness. These testing results determine the model's efficacy and foreshadow the model's role in the next and final stage. Finally, during the deployment stage, data scientists and stakeholders use the model on new data outside of the scope of the data set. New interactions during this stage might reveal the new variables and need for a different data set and model. Remember that the CRISP-DM model is iterative and cyclical. Deployment results might initiate revisions to the business needs and actions, the model and data, or any combination of these items. After completing all 6 stages, you'll have another business understanding meeting with the stakeholders to discuss the results. In CRISP-DM, the stage is not named. However, in John Rowland's data science methodology model, the stage is explicitly named the feedback stage. You'll continue the CRISP-DM process stages until the stakeholders, management, and you agree that the data model and its analysis provide the stakeholder with the answers they need to resolve their business problems and attain their business goals. In this video, you learned that CRISP-DM stands for Cross-Industry Standard Process for Data Mining. The CRISP-DM model consolidates the steps outlined in foundational data methodology into the following 6 stages: business understanding, data preparation, modeling, evaluation, and deployment. You'll continue the CRISP-DM process until the stakeholders, management, and you agree that the data model and its analysis answer the business questions.